Today in this lecture, we will discuss about the sulphur compounds. These are the compounds in which sulphur atoms combine with organic molecules. These are closely related to our daily life as in the form of petroleum fractions, as in the form of drugs, as in the form of chemical fertilizers, and as in the form of chemical research. So, we may say that in nature sulphur is essential for our life. Among 20 common amino acids, 2 are organosulphur compounds. The antibiotics penicillin and sulphur drugs both contain sulphur in their constituents. So, today in our lecture plan we will discuss about all these the categories of sulphur compounds, or we may say the organosulphur compounds in given module. As organosulphur compounds, their introduction, nomenclature, then structural features, then methods of formation and chemical reactions of thiols, thioethers, sulphonic acids, sulphur drugs as sulfonamides and sulfa-guanidine. So, viewers, sulphur containing organic compounds are known as organosulphur compounds, which are often associated with foul odors. Saccharin is one of the sweetest compounds, which is the derivative of organosulphur. According to the sulphur containing functional groups, organosulphur compounds can be classified as allicin. It is the active flavor compound found in crushed garlic. In this compound, we are seeing that sulphur atoms are trapped within the hydrocarbon chain, that is CH2. This is the hydrocarbon chain and these are the sulphur atoms trapped in between this chain. This is known as allicin. Next is methionine. It is also an amino acid containing a thioether. Here we are seeing that this is the sulphur atom trapped in this carbon chain, and we are having this carboxylic acid as the functional group and this NH2, that is amino group, and this is the chemical structure of methionine amino acid. So, now we will discuss the naturally occurring organosulphur compounds. In them, penicillin and cephalosporin are life saving antibiotics derived from fungi. Then gliotoxin, it is a sulphur containing mycotoxin produced by several species of fungi, act as an antiviral agent. Compounds like allicin is responsible for the odor of garlic. Now, we will discuss some compounds which are having sulphur in themselves, as here we are seeing that cysteine. In this, sulphur atom is at the terminal side of this chain. This is cysteine. In this molecule, sulphur atoms are trapped in between the chain. This is the biotin. It is the heterocyclic compound. In this, sulphur is trapped in this cycle. Here we are seeing that 2 hydroxyl groups are on terminal side of this chain, and these are the nitrogen atom, and at this side chain we are having sulphur atom. So, this is the example of glutathione. And next is methionine. Here we are having the amino group and carboxylic group, both are on terminal end, and this sulphur group is another terminal end of this hydrocarbon chain. It is the example of methionine. So, viewers, now we will discuss the organosulphur compounds in fossil fuels. The most common organosulphur compound present in all petroleum fractions is thiophene. The molecular formula is C4H4S. It is a cyclic and aromatic liquid. In addition, the heavy fractions of oil contain benzothiophene and dibenzothiophene. Most of the compounds are solids and smell like naphthalene. Many methylated dimethyl diethyl benzothiophene derivatives are present in diesel and fuel oils. Now, we will discuss the uses of organosulphur compounds. So, synthetic organosulphur compounds include polysulfones used in astronauts' transparent face shields. Polythiophenes, these are the materials possessing the metal-like ability to conduct electricity. In the form of agricultural chemicals, insecticides and organic solvents such as dimethyl sulfoxide and carbon disulfide, that is CS2. Another use is in the chemical research. Organosulphur compounds are valued reagents widely used for synthesizing new compounds. So, viewers, apart from that, we are having a long range of organosulphur compounds, which are as here we have the structures, molecular structures, name, then examples. Here we are having RSH, that is thiol, and the example is methane thiol. Another structure is RSR, that is sulphide, and the example is dimethyl sulphide. Another one is RSSR, that is disulphide, and the example is methyl disulphide. The next is RSSR, this is trisulphide because it is having 3 sulphur atoms. So, it is dimethyl trisulphide because dimethyl means 2 R groups are at the terminal ends and these are the 3 sulphur atoms. So, next is RSNR, that is polysulphides. N means L denotes the polymer numbers, or poly means many numbers of sulphide atoms in these compounds. So, the example is dimethyl polysulphide. R4S double bond O, that is sulfurane oxide. The example is tetramethyl sulfurane oxide. Next is R2C double bond S, that is thioketone, and example is thioacetone. Next is RCS double bond S, that is thioaldehyde, that is thioacetaldehyde. In this table we are seeing that if we have oxygen over here, then that is the example of aldehyde, but here we are having sulphur atom. So, sulphur is also known as thio, that is why it is also known as thioaldehyde, and the example is thioacetaldehyde. Next is Rn double bond C double bond S, that is the example of isothiocyanate, and the common example of this structure is methyl isothiocyanate. Next one is RSC triple bond N, that is thiocyanate, and example is methyl thiocyanate. Next is RCSNH2, that is thioamide, because this thio group is attached with this amide group. So, example is thioacetamide. Next is RSOH, that is sulfonic acid, and the example is methane sulfonic acid because this R represent methane. Next is RSO2H, that is sulfonic acid. Here we are having the difference that here we are using E and here we are using I. So, that is a little bit difference in the pronunciation, that is sulfonic acid and sulfonic acid. So, here we are having sulfonic acid and the example is methane sulfonic acid. Next is RSO3H, this is known as sulphonic acid and the example is methane sulphonic acid. So, viewers, now we will discuss nomenclature, structural features, method of formation and chemical reactions of thiols. So, thiols, in organic chemistry, thiol is an organosulphur compound that contains a carbon bonded sulfhydryl, that is RSH group, where R represents an alkane, alkene or other carbon containing group of atoms. So, thiols are the sulphur analog of alcohols, that is sulphur replaces oxygen in the hydroxyl group of an alcohol. So, the SH functional group itself is referred to as either a thiol group or a sulfhydryl group. So, many thiols have strong odors resembling that of garlic. Thiols are used as odorants to assist in the detection of natural gas. So, we know that natural gas in pure form is odorless. So, to detect the odor of natural gas we use thiols. So, the smell of natural gas is due to the smell of the thiol used as the odorant. Thiols are often referred to as mercaptans. The term mercaptan is derived from the Latin mercurium captans, that is capturing mercury, because the thiolate group bonds so strongly with mercury compounds. Thiols react with mercury to form mercaptides. So, viewers, now we will discuss the nomenclature of thioalcohols or thiols. Thioalcohols are sulfur derivatives of corresponding alcohols or alkyl derivatives of hydrogen sulphide. Now, we are having this table in which we are having molecular formula and common name, then IUPAC names of thioalcohols, that is CH3SH. The common name of this compound is methyl thioalcohol or methyl mercaptan. The IUPAC name is methane thiol. Next is C2H5SH, it is ethyl thioalcohol or mercaptan, and the IUPAC name of this compound is ethane thiol. In this compound we are having CH3 groups at the terminal and SH group at another terminal. The common name of this is isopropyl thioalcohol and the IUPAC name of this compound is propane 2-thiol. Why we are saying 2? Because this sulphur atom is combined with this carbon atom which is having number 2 position in the chain. There are several ways to name the alkyl thiols. The suffix thiol is added to the name of the alkane and is used by the IUPAC nomenclature. We have the example CH3SH, that is known as methane thiol. The word mercaptan replaces alcohol in the name of the equivalent alcohol compound. As we are having the example CH3SH, it is methyl mercaptan, as CH3OH is called methyl alcohol. So, OH is replaced by SH. The term sulfonyl or mercapto is used as a prefix, and we have the example mercaptopurine. Now, we will discuss the structure and bonding. The CSH angles approach 90 degree. In the solid or molten liquids, the H bonding between individual thiol groups is weak. The main cohesive force being van der Waals interactions between the highly polarizable divalent sulfur centers due to the lesser electronegativity difference between sulfur and hydrogen compared to oxygen and hydrogen. An SH bond is lesser polar than the hydroxyl group. Thiols have a lower dipole moment relative to the corresponding alcohol as per the electrochemical series. Now, we will discuss the physical property of thiols. First, we will discuss the odor. Many thiols have strong odor resembling that of garlic. The odor of thiols have often strong and repulsive, in particular for those of low molecular weight compounds. Human sweat contains RS3-methyl 3-sulfonyl hexane 1-ol, that is also known as MSH, detectable at 2 parts per billion and having a fruity onion like odor. Not all thiols have unpleasant odors. Say for example, furan 2-yl methane thiol contributes to the aroma of roasted coffee, whereas grapefruit mercaptan, a monoterpenoid thiol, is responsible for the characteristic scent of grapefruit. Most gas odorants utilized currently contain mixtures of mercaptans and sulfides with tertiary butyl mercaptan as the main odor constituent. The next physical property is boiling points and solubility. Thiols have lower boiling point and are less soluble in water and other polar solvents than alcohols of similar molecular weight. For this reason also, thiols and corresponding thioether functional group isomers have similar solubility characteristics and boiling points, whereas the same is not true of alcohols and their corresponding isomeric ethers. Now, we will discuss the methods of formation of thiols. We prepare thiols from alkyl halides, as here we are seeing that this is the ethyl chloride. When react with NaSH in presence of mild heat, we are having C2H5SH and NaCl. Next is from alcohol. Vapors of alcohols and H2S are passed over heated thiourea catalyst. Here we are having the equation chemical reaction C2H5OH, that is the example of alcohol, that is H2S in presence of thiourea catalyst, and mild heat we are having thiol and H2O. Next is the formation from Grignard reagent. In this, the Grignard reagent, that is C2H5MgX, when react with sulphur, we get this or intermediate compound when further changes in thiol, that is C2H5SH, and the side product is MgOHX. Now, we will discuss the chemical properties of thiols. First, we will discuss that how they react. So, thiols and alcohols are different in their reactivity, thiols being more easily oxidized than alcohols. Thiolates are more potent nucleophiles than the corresponding alkoxides. Sulphur is less electronegative than oxygen. Also, sulphur has less tendency to form double bond with oxygen, hence shows different chemical properties. Now, we will discuss the properties similar to alcohols. In them, the reactions of thiols with alkali metal, as here we are having this thiol molecule when reacting with this sodium metal, then we are getting sodium ethyl sulphide, that is C2H5SNA, and simultaneously hydrogen gas is evolved. Next is reaction with carboxylic acid and acid chlorides. Here we are having thiol, when react with acetic acid, then we get ethyl thioacetate and water molecule. Next is thiol, when react with acetyl chloride, then we also get ethyl thioacetate and the molecule of HCl. Now we will discuss the properties of thiols which are different from alcohols as mild oxidation. In them, thiol react with hydrogen peroxide. This is known as mild oxidation, and we have diethyl disulfide as the product and water molecule. In this product, we are having C2H5 and C2H5, 2 ethyl groups and 2 sulphur atoms. The next is strong oxidation. In it, when thiol react with oxygen, then we get ethane sulfonic acid, that is C2H5O3SH. Next is metal ion complexation. In them, thiols with metal ions form thiolates, which behaves as ligands to form transition metal thiolate complexes. Now we will discuss nomenclature, structural features, method of formation and chemical reactions of thioethers. Thioethers are sulfur derivatives of corresponding ethers, dialkyl derivatives of hydrogen sulfides. A thioether is similar to an ether except that it contains a sulfur atom in place of the oxygen. The chemical properties of ethers and thioethers are somewhat similar. A thioether is a functional group in organosulphur chemistry with the connectivity CSC. Thioethers, which are volatile in nature, have foul odors. Thioethers are sometimes called sulfides, especially in the odor literature, and this term remains in the use for the names of specific thioethers. So, CH3 whole twice S is called dimethyl sulfide. The example of thioether is C6H5SCH3 is methyl phenyl sulfide, but is more commonly called thioanisole, since its structure is related to that for anisole, that is C6H5OCH3. Here we are having O instead of S. Now we will discuss the nomenclature as per the table. Here we are having the compound, then common name and then IUPAC names. Here RSR, this is dialkyl thioether. The IUPAC name of this compound is dialkyl sulfide. Next is CH3SCH3, it is dimethyl thioether, and IUPAC name of this compound is dimethyl sulfide. Next is C2H5SC2H5, it is diethyl thioether and known as diethyl sulfide. Now we will discuss the structure and properties of thioethers. Thioethers are characterized by their strong odors which are similar to thiol odor. This odor limits the application of volatile thioethers. In terms of their physical properties, they resemble with ethers but are less volatile, having higher melting points and less hydrophilic in nature. Now we will discuss the methods of formation of thioethers. First, we will prepare them from alkyl halides. Here ethyl iodide when react with potassium sulfide, then we get thioether, that is C2H5SC2H5 along with Ki molecule, that is potassium iodide. Next is from thiosalt and alkyl halide. Here we are having ethyl iodide, that is C2H5I when react with sodium ethyl mercaptide, that is C2H5SNA, we get thioether and NaI, sodium iodide. Next from thiols and alkenes, this is the alkene CH2 double bond CH2 when react with ethane thiol, that is C2H5SH, we get thioether. Now we will discuss the chemical properties of thioethers. First is reaction with alkyl halide. In this reaction, thioether when react with C2H5I, that is alkyl halide, we get triethyl sulfonium iodide. Here we are having triethyl, that is C2H5, C2H5 and C2H5. So thioethers are readily alkylated to give stable sulfonium salt such as trimethyl sulfonium iodide. Next is the oxidation properties of thioethers. First we will discuss the mild oxidation. In this oxidation, thioether react with H2O2, that is hydrogen peroxide, and we get diethyl sulfoxide. Next is oxidation. Thioethers can be easily oxidized to the sulfoxides, that is RSOR, which can themselves be further oxidized to sulfones, that is RSO2R. Hydrogen peroxide is a typical oxidant in this oxidation. Next is strong oxidation. In this oxidation, thioether when react with the strong oxidizing agent, that is HNO3, we get diethyl sulfone. Here sulphur atom is combined with these two oxygen, that is why known as sulfone. Next is addition of halogens. In it, thioether when react with Br2, that is halogen, then we get diethyl sulfide dibromide, that is diethyl, two ethyl groups, and these are two bromide groups, that is why it is known as diethyl sulfide dibromide. Next is hydrolysis. In this, thioether when react with water molecule, then we get ethanol, that is C2H5OH. So, special class of thioethers are thiophenes. Now, we will discuss the special class of thioethers, that is thiophenes. Thiophenes are a special class of thioether containing heterocyclic compounds. They are non-nucleophilic because of their aromatic character. As a consequence, thiophene exhibits few properties expected for a thioether. Thiophene is non-nucleophilic at sulfur and it is having sweet smell. Thiophene upon hydrogenation gives tetrahydrothiophene, that is C4H8S, which indeed behaves as a typical thioether. Now, we will discuss the sulfonic acid. Sulfonic acid is a member of organosulphur compounds with the general formula RS double bond O whole twice OH, where R is an organic alkyl or aryl group and the S double bond O whole twice OH a sulfonyl hydroxide group. A sulfonic acid can be thought of as sulfuric acid with one hydroxyl group replaced by an organic substituent. The parent compound with the organic substituent replaced by hydrogen is the hypothetical compound sulfurous acid. Salts or esters of sulfonic acid are called sulfonates. Although both alkyl and aryl sulfonic acids are known, most of the applications are associated with the aromatic derivatives. Now, we will discuss the sulfonic acid in various forms, as in the form of detergents and surfactants. Detergents and surfactants are molecules that combine highly non-polar and highly polar groups. In the form of dye, many dyes are produced or processed via sulfonation. Sulfonic acids tend to bind tightly to proteins and carbohydrates. Many dyes are sulfonic acids. Paracrecidine sulfonic acid is used to make food dyes. Sulfonic acid in the form of acid catalyst. Being a strong acid, sulfonic acids are also used as catalysts. The simplest example are methane sulfonic acid, that is CH3SO2OH, and paratoluene sulfonic acid, which are regularly used in organic chemistry as acids which are soluble in organic solvents. Another example of polymeric sulfonic acid is also useful. Doxyresin is sulfonic acid derivative of polystyrene and is used as catalyst and for ion exchange in water softening. Now, we will discuss the nomenclature of sulfonic acids. Sulfonic acids can be named most readily by naming the carbon groups as a separate word followed by the word sulfonic acid. Here we are having this phenyl group and this is SO3H, that is sulfonic acid. So, the name of this compound is phenyl sulfonic acid. Next is taurine. This is a bile acid and one of the few naturally occurring sulfonic acid shown in uncommon tautomer. Here we are having the chemical structure of taurine. Here this is the carbon chain having terminal amide group and this is the sulfonic acid group, that is SO3H. Next example, PFOS, that is perfluorooctane sulfonate. It is a surfactant and a controversial pollutant. This is the chemical structure. Basically, it is polyfluorocarbon compound having SO3H, that is sulfonyl group on this terminal. Perfluorooctane sulfonic acid or perfluorooctane sulfonate, that is PFOS, is a man-made fluorosurfactant and global pollutant. PFOS was the key ingredient in Scotch Guard. It is a fabric protector and numerous stain repellents. PFOS compounds can be found in some impregnation agents for textile, paper and leather, in wax, polishes, paints, varnishes and cleaning products for general use, in metal surfaces and carpets. Next compound having sulphonic acid is toluene sulphonic acid. It is a widely used reagent in organic synthesis. In this compound, we have sulphonic acid group, that is SO3H, and this is the toluene structure. This is the representation of CH3. So, the compound is known as toluene sulphonic acid. Next is nepheone. It is a sulfonated tetrafluoroethylene based fluoropolymer copolymer. It is used in fuel cells. Here we are having the structure of this compound. We are seeing that fluorine is trapped in this carbon chain and having three types of compound, that is X, Y and Z, and this is the terminal SO3H group, that is sulfonyl group. This is known as nepheone. Now we will discuss the structural features of sulphonic acid. The structure of sulphonic acid is illustrated by the prototype methane sulphonic acid. The sulphonic acid group, that is RSO2OH, features a tetrahedral sulfur center, meaning that sulfur is at the center of 4 atoms, 3 oxygens and 1 carbon. The overall geometry of the sulfur center is reminiscent of the shape of sulphuric acid, that is SO4, and these are the 2H. So, we may say that H2SO4. Now, we will discuss the methods of formation of sulphonic acid. First, by sulfonation. Sulphonic acid is produced by the process of sulfonation by using the sulfonating agent sulphur trioxide. Here we are having the chemical reaction. This is C6H5R, that is arene. When react with SO3, then we get alkyl benzene sulphonic acid. In this reaction, sulphur trioxide is acts as electrophile, and this reaction is known as electrophilic aromatic substitution. Next is by oxidation. Thiols can be oxidized to form the sulphonic acids, as these are the thiols. When react with oxygen, then we get RSO3H, that is sulphonic acid. Next is by electrophilic fluorination. Sulphonic acids as perfluorooctane sulphonic acid are prepared by electrophilic fluorination. In this reaction, when octane sulphonic acid is fluorinated, then the formation of perfluorooctane sulphonic acid takes place. Here we have the chemical reaction C8H17SO3H, that is octane sulphonic acid. When react with 17 molecules of fluorine, then we get C8F17SO3H, that is perfluorooctane sulphonic acid. Here this H17 replaced by this F17. Now we will discuss the chemical properties of sulphonic acid. Sulphonic acids are much stronger acids than the corresponding carboxylic acids. As methane sulphonic acid is about 1 million times stronger than acetic acid, because of their polarity, sulphonic acids tend to be crystalline solids. Because of their high acidity, sulphonic acids are often soluble in water or exhibit detergent-like properties. Next is esterification. Sulphonic acids can be converted to esters by the process of esterification. This class of organic compounds has the general formula RSO2OR. Sulphonic esters are considered good alkylating agents in organic synthesis. Such sulfonate esters are often prepared by alcoholysis of the sulfonyl chlorides. By using this chemical reaction, we get the sulfonate ester. In this reaction, RSO2Cl, that is sulfonyl chloride, when react with ROH or alcohol, then we get sulfonate ester, that is RSO2OR1. Next is halogenation. In halogenation, sulfonyl halides groups occurs when a sulfonyl functional group is singly bonded to a halogen atom. They have the general formula RSO2X, where X is a halide. Next is displacement. An early method for producing phenol involved the base hydrolysis of sodium benzene sulfonate, which can be generated readily from benzene. Here we are having this sodium benzene sulfonate. When react with NaOH, then we get phenol, that is C6H5 along with Na2SO3 and water molecule. Now we will discuss the sulfur drugs. We are discussing here two types of sulfur drugs as sulfonamide and sulfaguanidine. Here we are having the structure. This is the structure of sulfonamide and this is the structure of sulfaguanidine. Now we will discuss one of the sulfur drugs as sulfonamide. Sulfonamide is the basis of several groups of drugs. Sulfonamide are also called sulfur drugs or sulfur drugs that contain the sulfonamide group. So, sulfonamide drugs were the first antibiotics to be used systematically and paved the way for the antibiotic revolution in medicine. The first sulfonamide trade name was Prontosil. The active molecule sulfonamide or sulfa had first been synthesized in 1906 and was widely used in the dye making industry. Its patent had since expired and the drug was available to anyone. Allergies to sulfonamide are common, hence medications containing sulfonamides are prescribed carefully. Because sulfonamide displaces bilirubin from albumin, it is an important potential side effect of sulfonamide use. Now we will discuss the preparation of sulfonamide. Sulfonamides can be prepared in the laboratory in many ways. The classic approach entails the reaction of sulfonyl chlorides with an amine. Here we are having the chemical reaction, that is RSO2Cl, it is sulfonyl chloride. When react with this amine, then we get sulfonamides, that is RSO2NR2 along with HCl molecule. Now we will discuss the structure of sulfonamide. Sulfonamides are compounds which have a general structure represented by structure. In this structure, R1 may be alkyl, aryl or heteroaryl etc. R2, R3 may be hydrogen, alkyl, aryl or heteroaryl groups. Here we are having, that is R1, R2, R3, these may be hydrogen, alkyl, aryl or heteroaryl groups, and these are the oxygen and this one is oxygen trapped in between all these groups. Here we are having the list of sulfonamide drugs in different categories as child antibacterial drugs, antimicrobials. These are further having 3 categories, that is short acting, intermediate acting and long acting. Then we are having another group of diuretics, then another group is sulfonylureas, that is anti-diabetic agents. Now we will discuss sulfonamide based compounds. It is the hydrochlorothiazide. It is a drug that features both acyclic and cyclic sulfonamide groups. Next is sulfanilamide. It is a compound that foreshadowed the development of sulfur drugs. And finally, we have sulfamethoxazole. It is a widely used antibiotic sulfur drug. Now we will discuss the uses. Sulfur drugs are widely used for conditions such as acne and urinary tract infections and for the treatment of infections caused by bacteria resistant to other antibiotics. Sulfa had a central role in preventing wound infections during the war. American soldiers were issued a first aid kit containing sulfa pills and powder and were told to sprinkle it on any open wound. The sulfanilamide compound is more active in the protonated form. The drug has very low solubility and sometimes can crystallize in the kidneys, which creates the side effects. Next sulfur drug is sulfaguanidine. Now we will discuss about the sulfaguanidine. Sulfaguanidine is a sulfonamide. Also, sulfaguanidine is a sulfanilamide anti-infective agent. It has a spectrum of antimicrobial action. It is used to treat bacillary dysentery, also as raw material of sulfadiazine drugs, as auxiliary material for other drugs. Now we will discuss the method of formation. First is condensation method. When condensation of N-acetyl sulfonylyl chloride with guanidine takes place and resulting product is hydrolyzed by an alkali, then the formation of sulfaguanidine takes place. Here we are having the chemical reactions. It is the structure of N-acetyl sulfonylyl chloride, that is ASC, when react with this guanidine, that is CNH, NH2, NH2, the removal of HCl takes place. Here we have the HCl molecule and this NH directly attach over this SO2 group and we have acetyl sulfa guanidine, that is this moiety. When react with further NaOH, then we have CH3CONa as byproduct, and finally we get sulfa guanidine in the form of sulfur drug. It is a white fine crystalline powder soluble in dilute mineral acids, very slightly soluble in water and ethanol, slightly soluble in acetone. It is commonly used in the treatment of intestinal infections, specifically in bacillary dysentery. So now it is the time to conclude our whole unit of organosulphur compounds. In this unit, we have discussed introduction of organosulphur compounds, their nomenclature, structural features, along with the methods of formation and chemical reactions of thiols, thioethers, sulphonic acids and sulphur drugs as sulfonamides and sulfaguanidine, along with their uses. I hope you enjoy this unit of organosulphur compounds a lot. Thank you.